Okay, it's time for me to test you already. I need you to pause the video, and I need you to draw me the structure of glucose that you just learned. So pause the video, attempt it, and see if you get it correct. Alright, so let's double check and see if your chemical memorization is up to par. So glucose is a 6-carbon chain. 1, 2, 3, 4, 5, and 6. Glucose is a aldehyde, so we see this double bond O up there at the top. And then every one of these carbons needs an OH group on them, right? So we said that for it to be glucose, it needs to be right, then left, then right, then right. And the remaining ones of these are hydrogens down the board. So this is the structure for glucose. We call this the Fischer projection. So this is what we refer to as the Fischer projection or the Fischer structure. And the Fischer is the shortcut method other than the wedged and dashed system. So how does the Fischer and the wedge and dash compare to each other? Well, let's get some practice here. So I'm just going to draw the structure of glucose all over again. So there's 2, 3, 4, 5, and 6. And then this carbon, we have OH to the right. And this one, we have it to the left. This one, we have it to the right. This one, we have it to the right. This one, it doesn't really matter. We see H's, 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 H's. So how does the Fischer and the wedge and dash relate to each other? Okay, well, what you need to understand with these structures, orientation is very important. Why? We'll see a little bit later. But orientation is a very important aspect to these structures. So if I take a look at the structure for glucose, this backbone, the way that we've drawn it, there's something that's understood here. And what is understood is that all of these hydrogens and all of these OH groups, they're pointed toward you. So they are all on a solid wedge, every one of them. Now look how long it's taken me to draw these solid wedges just to show you that these hydrogens, and they don't really happen here at the bottom, but these hydrogens and these OH groups are pointed towards you. Now notice I didn't do anything to the top and I didn't do anything to the bottom carbon. There's a reason for that, and we'll talk about that reason in another video. But all of the middle carbons in the backbone itself, not the head and the tail, but the backbone, all of those middle carbons, the H and the OH group, are pointed toward you if you made the model kit. The head points away, so I'm going to draw that as a dash. And the tail points away, so this CH3 group that's down here, or this CH2OH group that's down here at the bottom, that whole group points away from you as well. So we can kind of get a sense of some stereochemistry here, at least some 3D orientation, so we can orient ourselves. Again, the head and the tail go away from you, and the OH groups and the hydrogens on the backbone point toward you. That is what we call the wedged and dash structure. So wedge and dash. Well, very early on, we knew how crazy we were to draw these solid and dashed wedges all over the place. So we modify the structure, and we just understand that the H's and the OH groups, if they're drawn in this way, in the Fischer projection, point toward me. And the head and the tail point away from me. The same thing will hold true for a polyhydroxy ketone. So let's take a look at our first polyhydroxy ketone. What would it look like? Well, okay, let's take, a couple of carbon chains. 1, 2, 3, 4, 5, and 6. And a polyhydroxy ketone would be a ketone functional group, right? So I can't put the double bond O up at the top. That would be an aldehyde. So I would put it here. So there's a ketone. And all of the other carbons, well, they all have 4 bonds in total, right? So we got to do this number and that number and this number and down here at the bottom. And all of these carbons, except for the head and the tail, should have a H and an OH group. So that means that this carbon should have a HOH. So let's just draw OH and H. This carbon should have an OH and an H. So let's put H here and OH there. This carbon should have an H and OH. So let's put it here and there. And the head and the tail, well, they need OHs as well, so we'll just put OH group here, and we'll put an OH group down here, and the 2 remaining bonds are just for hydrogens. Okay, so there's a polyhydroxy ketone. This polyhydroxy ketone, we could go through and we could name it if we wished. Right? A ketone ends in an ONE ending. There's a 6-carbon chain here, so this is hexanone, and this is 2-hexanone because that's where the ketone functional group happens. Not only that, but on carbon number 1, on carbon number 3, 4, 5, and 6, we see an OH group, so we can go through and name the substituents just like before as well. I don't really want to provide an IUPAC name for it though. What I do want to provide is a common name, something that it's known for. So this structure is called fructose, fruit sugar. It's a polyhydroxy ketone. This is the Fischer projection of a polyhydroxy ketone. Not only that, we need to understand that the OHs and the H's in the backbone point toward us, and the CH2OH at the top and the CH2OH at the bottom point away from us. The head group and the tail group point away. The carbon and everything that's attached to that carbon points away at the top, and the carbon at the bottom and everything on that carbon points away as well. Now, some people, they don't really like to draw out these hydrogens and these OHs the way that I've done here. They like to condense it a little bit, and we can quickly condense these without a problem. And what we would do is that we would just erase these bonds, right? I'm erasing 2 hydrogens here, and instead of drawing the actual bonds, I'm just going to write CH2, and then I can just erase that OH bond as well and just kind of sandwich it here right on top. So we can kind of clean up these structures a little bit if we want. So this entire group, CH2OH, the carbon, the last carbon, everything attached to it points away. The same thing's going to happen up here at the top. I can kind of condense this down if I want. There's 2 hydrogens that I've erased. So this is CH2. And then I'll erase the OH group up here at the top and just continue on with it. And this top carbon and everything attached to it points away. That is the stereochemistry with this structure. It is very, very important. Well, if I can do that with the polyhydroxy ketones, why didn't I do it with the polyhydroxy aldehydes? Well, you can. You can take this structure here and you can kind of condense it down. So we'll erase those 2 hydrogens and we'll just write CH2. And we'll erase that OH group down here at the bottom and just continue it out a little bit longer. So CH2OH at the bottom. I can do the same thing here if I want. It's not an issue at all. It's just really some bookkeeping, cleaning stuff up a little bit, making sure it all looks okay. So there's the Fischer and Wedge comparison between a polyhydroxy aldehyde, a polyhydroxy ketone, and what these solid and dashed wedges are supposed to represent and mean. Okay, so we've kind of tackled the first aspect of organic chemistry in the biological world. We're quickly seeing that structure and the way it's oriented is very, very important. We have already, within the first 20 minutes of the lecture series, have stressed nothing but stereochemistry. One after another after another. Stereochemistry is very important. You have to imagine your body as a keyhole. And the keys that we insert to make the door open, or the things that we insert in our bodies to make it work, they have to fit a proper way. The key has to unlock the door and it has to open the door up. And if we have the wrong key, nothing's going to happen. The same thing is going to happen to these biological molecules. These molecules are the keys. And once you insert the key in, if the key doesn't fit in the right way, nothing's going to happen. It's not going to do anything for us at all. So we have to ensure that the keys that we use are fitting inside of the keyholes, opening these doors up to make these molecules do what they were meant to do. And that's very important, and that all leads into stereochemistry. The orientation of these molecules, the way they're made, the way they're structured. If I do just one thing to this structure, and we'll see it later on in the video series, but if I switch or if I modify this structure in a certain way, I get a carbohydrate that no longer is a carbohydrate. It's not going to do anything for me as far as my body goes, and it's useless. And that's something that we don't want to happen, right? So Fischer and Wedge, stereochemistry, the shape and the structure of a polyhydroxy ketone, polyhydroxyaldehyde. Here you go. This is the introductory to the world of biochemistry, and in the next video we'll go through and we'll talk about more of the classification scheme concerning the carbohydrates.